But I'm going to talk also about programming distributed systems with consensus and without consensus. So I'll talk about consensus, which is a really important algorithm, which is needed to make the internet work. Then I'll tell you kind of a nice story. I like the stories. And then I'll talk about the concepts where we replace consensus by another kind of consistency, convergent consistency. So based on strong eventual consistency. So this was defined by Mark Shapiro. And there's data types that implement this form of consistency without consensus. And there's also a theorem. I'm going to present 5 theorems during this talk, okay? It's not just practice. And we have scaled it up to 1,000 nodes. So it's both theory and practice. And what I did in the whole business, is composing CRDTs, so the Lasp work. So a little bit of context. So large fault-tolerant servers, very important on the internet, okay? Amazon, that's why Bezos is so rich. But the replicas have to be consistent. So typically it's using consensus algorithm for this. And a little bit of history, can consensus be implemented on the internet? This was not so obvious. It was first proved in 88, and the Paxos algorithm by Lasp in 1989. So you could say that the internet from 1970 to 89 was baby internet. It only became grown up since 1990 when it had consensus. But consensus is not really so nice. It's kind of a brute force algorithm. It forces nodes to accept decisions. So the question, can we have consistency without consensus? And the answer is we can. And this leads to another way of achieving consistency using through monotonic convergence. So the convergent data types, CRDTs, were invented by Mark Shapiro and his colleagues. And the theorem that tells you exactly when this can be used, the CALM theorem, was introduced by Peter Alvaro. And the final point, it's actually used a lot in industry, this thing. Okay, it's not just theory. So this is the typical big internet. So I didn't make this slide. This comes from the Raft talk. You have a replicated server, lots of nodes. They have to be consistent with each other, of course. This is called a replicated state machine. And typically using consensus, this consensus algorithm to guarantee that these nodes are consistent, okay? So this is a very standard thing on the internet. It's all over the place. So what is consensus? I've talked about consensus. It's a distributed algorithm where all the nodes propose a value, you run the algorithm, and then they all agree on one of those values. So they have to agree, okay? But the internet is not so simple. It's called what's called a partially synchronous system. And it's kind of very hard to write algorithms for this. So it starts out being asynchronous, which means there's no bounds on message travel time. And eventually, which means after finite time, it becomes synchronous, where there are bounds. But the problem is you don't know when this happens, and you don't know the bounds. That's the internet. That's how, because of how the internet is built, the hierarchical structure. And any very large system will be partially synchronous. So this was actually a big question. Can we implement consensus on the partially synchronous system, the internet? And many people worked on this for a long time. And so in 1989, Leslie Lamport presented the Paxos algorithm, which allows you to do consensus on n nodes. There's only one condition, that the majority of the nodes have to be correct. Okay, so less than n over 2 failures. And this has been proved to be the theoretically best result. So Paxos kind of opened the door to really big, huge algorithm internet applications. Okay, but now, so that all sounds very nice. But now I want to tell a little story. And I go now to an analogy. Look at internal combustion engines. Okay, motors still use a lot today, converting gasoline to mechanical work. So gasoline is a very high quality energy, mechanical work also, but it makes a detour through heat, which is very low quality energy. So this is a brute force approach. You make the gasoline explode, And then you try to convert some of that heat back to mechanical work, and that's inefficient. And there's a theorem, Carnot's theorem. So no engine operating between two heat reservoirs, low and high, can be more efficient than a Carnot engine that's running between the same two reservoirs. So the maximum efficiency is basically 1 minus TL over TH in Kelvin. So which is not so high, even after a century or more of internal combustion. It's like what, 40%, or it's still pretty low, okay? It's better than steam engine, but it's still pretty low. So this is my view also of consensus. Okay, so consensus. Here's the algorithm. Nodes propose, and then they decide on the same thing. There's an explicit choice. All nodes propose, the algorithm picks a value, and all nodes use the value. But that's brute force. This algorithm forces the node to use that value, and it's also high latency, and it's non-deterministic. This is a very nasty property in computing systems, because we don't really know which value is going to be chosen. It depends on a lot of things, okay? And as I mentioned before, a majority of the nodes must be correct. So I don't like this algorithm. Even though Lamport is a genius, I still don't like this algorithm because it's brute force. Question, is there a better way to do consensus and to do big internet applications? Well, the analogy for internal combustion is electric motors. An electric motor converts electrical energy, which is very high quality, to movement, also high quality, no detour through low quality, high efficiency, So more and more cars are becoming electric. Well, we can actually have an analogy in consensus. We can have another kind of consistency, which I call convergence. It obtains consistency by monotonic convergence. So the nodes will actually converge to the same value, no detour through a brute force non-deterministic choice. So this is actually deterministic. Okay, so that sounds very nice, right? But can it really work in practice? So electric motors, convergence, does it really work? Well, electric motors were already existing around 1900, but they were not practical because the batteries did not store enough energy. But today they're practical. Practical. And what about consensus? Well, we will see. I will show you and try to convince you that convergence is also practical. Okay? But you still sometimes need consensus, and I'll try to make very precise exactly when you need it. But most fault-tolerant replicated distributed computation can be done without consensus, and we will show how that's done. Okay, so I will explain now the consistency model, and then the practical data structure that implements it. So what I call this convergent consistency. But let's go back to first principles. We want to build distributed systems, and they should be easy to program and efficient. Okay, those are kind of conflicting goals. So the easiest to program is strong consistency, linearizability, which is exactly like sequential machine, but inefficient, very slow, and requires consensus. On the other direction, if you want a very efficient thing, you can do eventual consistency, where all operations just go through, eventually complete, but actually very hard to program with. Can we get the best of both worlds? Actually, we kind of can now. With convergent consistency, it's as simple as functional programming, and it's efficient. Okay? So to give you kind of the fundamental explanation, a distributed system is a collection of computing nodes that behaves like one system. And what does that mean? It means there's a consistency model. So in red, I put here the consistency model. And in order to make that work, you need some algorithm. You need some rules, code running. And that in blue, that's what's called the synchronization algorithm. For example, a reliable broadcast algorithm guarantees all or none. All correct nodes will deliver the message, or none, nothing else. So there's kind of an atomicity property. So this is an example. But how far can we go in general, okay? So we want the consistency model to be very strong for that, because that's easy to program, like linearizability. But we want efficiency, so we want the synchronization algorithm to be very weak. But But we do need some, because if you have no synchronization, there's no consistency. So you do need some. What's the least that we can get away with? Okay. So here's an approach that's used a lot still in industry. Actually, less than before, because the industry is moving to more functional style, like in big data. But this is, it was still, and is still used a lot, many applications, like in Cassandra database. So you have a bunch of replicas. Let's say you do reads and writes, okay? You can do any kind of requests concurrently, and the write will be eventually replicated. The read will be eventually handled by one replica. So there's many things happening in flight, and all we can say is that eventually the read will see the write. If you do a write, then a read, will the read see the write? Sometimes yes, sometimes no. So there's a finite interval in time when the system's kind of erratic. And that's inherent. That's part of eventual consistency. So it's kind of nasty to program with, but very efficient. Okay. But in convergent consistency, we have a better one. So the Mark Shapiro and his colleagues invented another consistency model, which they called strong eventual consistency. And it's very interesting. So you have n replicas, and the updates are sent. So they're all updated, and they receive them in any order. Each replica receives the updates in any order. And the point is that if they receive the same set of updates, no matter what order, state will be equivalent. That's pretty amazing. So it's like order independent. And the only synchronization algorithm is replica-to-replica communication. That means the replicas have to occasionally send information to each other. Nothing more than that. So this gives you, it's a very interesting model, and it's really powerful. So if you can implement this, then you actually are programming as functional programming. So distributed systems people don't really understand programming languages, but in fact, programming languages are very important, and functional programming, so programming that's similar to lambda calculus, is actually very efficiently realizable. Okay, so Mark Shapiro and his colleagues invented a model called conflict-free replicated data types, CRDT, that actually implement strong eventual consistency. Okay, and they exist for many types. They can be generalized and decomposed. And because of this convergence aspect, I call this convergent consistency. Okay, so let me now talk about the CRDTs, which implement strong eventual consistency. So we want to build data structures, strong eventual consistency. So here's one way. This is called a state-based CRDT. Now there's another way called operation-based CRDT, but I will just show you one. So there's different ways, but this is one of the most common ways. So a CRDT is a triple. So you have n state values. So the replicas exist on n nodes, and each of these values is actually an element of a join simulatus, which I will explain in a minute. You have a query function where you can read the value of a replica, and a mutate, an update function, which basically inflect. So on the join, you have this partial order. So when you mutate a value, all the old information is still there. It's only moving up the ladder. So it's monotonic. So you're only adding information. You're not ever changing anything. Everything that's true remains true forever. And occasionally the replicas talk to each other, and each replica sees the replica of another node, as J, for example, and does a join. So basically, the nodes will kind of chat between each other and update each other, and each node can be mutated. So this actually is convergent. This satisfies strong eventual consistency. It's basically because of the properties of the mutator and the join simulatus. Okay, just a little bit of mathematics. So the state-based CRDT is based on a join simulatus. So a join simulatus, so here's an example. So each of the nodes here is a value. It's a partially ordered set, but you can compute least upper bound. So you can always move up. If you have any two values here, you can join them and find another value which is the least upper bound, and that's always possible. And all operations are always moving up the lattice. So all these things are monotonic. Okay, so that's the CRDT. Let me now give you an actual example. So there's many CRDTs exist, and some really, really clever ones. But I will show you one non-trivial one called the observed remove set. So this basically implements a set where you can add and remove elements, and it's distributed, fault-tolerant. So you do a sequence of adds and removes. It's like a sequential set, but in the distributed system, it's a little bit more general because of distribution. If you do a remove, you will actually only remove the ones that were added in the causal history. Okay, so that's because it's distributed. That's okay. And if you do concurrent add and remove, the add has precedence. So I'll show you how this set is implemented as a CRDT. And the intuition is, whenever you do an operation, an add or a remove, you will create a unique value, a unique identifier of this operation. Now you will tag that, and you collect those, and with that you can determine whether the element is or not in the set. So here's an example of how it works. So I have three replicas here. So the time is going from left to right. Here, for example, I do an add one into the set. So this is a set of integers. So the set actually stores triples. So the one, the set of adds, the add tags, and the set of remove tags, okay? And the element is in the set if the add is minus the R is not empty. So add, this is empty, so the one is in the set, okay? So here also I add one. So I have 1B, and then there's these joins, which is the nodes kind of chatting between each other, so sending information back and forth. So this 1B empty will actually move to R2. But if I now remove one, then it will take this A and put it as the R. That means B minus B is empty. So the one is no longer in the set. Okay. But now look very interesting. If there's a join here, we will now have the two adds and removes here. We have one A, B, B. Yeah? We take the unions. So the one is actually still in the set because this add is not in the causal history of this remove. Okay. And the joins keep adding information. Eventually, all three replicas contain the same information, and they all agree that one is in the set. Okay, so all updates, both adds and removes, cause monotonic increase in the set. And the theorem proved by Shapiro and some very nice people I know, Nuno Bragusa, Carlos Baquero, Marek Zawirsky, is that a state-based CRDT will satisfy strong eventual consistency in all distributed executions. Okay, this was in 2011. Okay, so that's the CRDT. It can achieve consistency without having to do consensus. And it's used in industry. So actually, there are a number of libraries existing of CRDTs. So one of the most common, famous ones or well-known used ones is this REAC database done by a company called Basho. Unfortunately, Basho no longer exists because of stupid management decisions, but REAC still exists. And all these companies here are actually using CRDTs in industrial applications. So production quality CRDT libraries. Okay, so this is nice, right? But it's not completely solving the problem because of what I will tell you. So can now CRDTs replace consensus? So remember, consensus in a replicated server, you have n programs and they run and the consensus forces them to agree. Can we do that, CRDTs? Well, not quite. Because the replicated server runs an arbitrary program, but each CRDT implements just one data type. we would actually have to have a custom CRDT that exactly fits the data used by the program, or you shoehorn it somehow into an existing CRDT. So there's no general solution to this, but we're getting close. Okay, so there's three. So this problem is being attacked in three directions. One, there are a large number of practical, very smart and clever CRDTs. So this is a big research topic. There's many of these. Second, there is now research on how you create arbitrary CRDT-like entities that are obeying strong eventual consistency. And the third point is composing CRDTs. If you have an application with lots of variables, well, you compose them all together. And that's where the contribution, where my contribution comes in. So this is what I did with my student, Christopher Mickeljohn. These other two areas are also very, very active. So there's many CRDTs that exist. So maps, for example, recursive graphs, file systems, sets. So I showed you the observed remove, but the really clever one I didn't show you, which is called the OR swap, the OR set without tombstones. This one is really nice because it does not need garbage collection. Now you will notice that the monotonic growth seems like you will keep adding and adding. Eventually you have to garbage collect. Well, the OR swap doesn't have this problem. It's incredibly powerful. So the OR swap, but it's maybe too complicated because it basically uses causality to have a very compact representation internal to the CRDT. So there's many CRDTs that exist. In the second direction, there's also custom data types. So this is work going on. Actually, there was people in the VUB for University of Brussels who worked on this. Strong, eventually consistent replicated objects. So SECROs. So you guarantee strong eventual consistency. You construct something, but it's a little bit slower, okay? But there's no restriction. But if you implement in a certain way, you can actually get it to be competitive. Okay, so this is fairly recent work, and it still was improved with using an SMT solver statically to improve even the behavior of the system. So this is getting close to CRDT, general CRDT, custom ones. Okay. So new CRDTs, and more generally in SQL databases, CRDTs which have undo, very efficient implementations, what's called delta state CRDTs, also synthesizing using verification techniques, and sliding windows, so more CRDTs on streams, and then composition of NIST maps, and Lasp, where you actually combine sets and counters. So this is the one that I'll explain to you in a few minutes. And then programming, so monotonicity types, mixed consistency, consistent reactive, so more smarter ways of programming. Okay, so now I want to tell two things. One, I said we want to replace consensus. Consensus is brute force, okay? But it works pretty well, but it's brute force. So what are the limits of convergent consistency? So the limits were shown theoretically for what's known as the Calm theorem. So I won't go into the details of how it's proved, but CALM is an acronym meaning consistency as logical monotonicity. So this puts a strict condition on when you can do coordination free, when you can do a system which does not need consensus at all. So it's coordination free if and only if it is monotonic. Monotonic means the way you're executing, you never change anything. You only keep adding information. So it's basically like functional programming, okay? So the distributed computing system that obeys the CALM theorem looks something like this. Inside here, you have only monotonic execution, which is functional, and there's a boundary. And outside of this boundary, execution is non-monotonic. So distributed programming can be coordination-free if it's monotonic. But the real world is not always monotonic. Very often it's not. So there's a boundary, and you have to cross this boundary, okay? Notice functional programming is monotonic, and CRDTs are also monotonic. So if you can already do distributed functional programming. If you add CRDTs to this, it becomes fault tolerant. Okay? So when I talk to people, they don't believe that you can do functional programming in a distributed way. So I try to prove it to them in one simple slide. So if I have a functional program, so functional programming like in Haskell or Scheme, you have pure functions only based on lambda calculus. And there's a very nice property called Church-Rosser that no matter what reduction order you do, you get the same result. So this is completely deterministic. Okay, now the first step, you can make it concurrent. If you run these two guys in different threads, and you have a composition. So Z is G of Y, and Y is F of X. So this G requires the result of F of X. This is a data flow synchronization. So this function application will wait until that one appears. Okay? The read waits until the variable is bound. And Church-Rosser still holds. It's still deterministic because we're changing the reduction order fine. Now, this can also be distributed. These two guys can be running on different computers. So this function is applied on node 1, and node 2 requires Y. So there's a message being sent. Notice the message is asynchronous, which means you don't wait for a reply. You just send it and let it go. So asynchronous message passing is purely functional. So that's the thing. Many people don't understand that, or they would even dispute that, but it's clearly true. And if you add CRDTs to this, then it becomes fault tolerant because you have consistent replicas. Okay, so in general, so this whole approach means that there's a different way of building distributed systems. Okay, so here's my distributed system, and here's a program. Now, part of this program is monotonic. This part here with this blue boundary, and this boundary is very crucial. Another part is non-monotonic, okay? And the question is, can we reduce the size of this one by bringing them into the monotonicity boundary? So for example, so this is a whole research agenda. If you have a microservice architecture, which is very popular, lots of small pieces called microservices connected together. Today, right now, that's very popular. But the people building them, they have never heard of monotonicity, okay, or non-monotonicity. Most of them are non-monotonic. Not all, some are pure functions, so they're monotonic, but most are non-monotonic. But if you would rewrite them to be monotonic, and that's very often possible, they would all move inside that boundary, and you would not need consensus. Okay. So this is, in my view, a research agenda is to bring as much as possible the execution inside that boundary. Okay. And now I get finally to the part where I made a contribution with Chris. So we built a system called Lasp, which is an acronym inspired by Lisp, lattice processing. Whereas Lisp is list processing, here we called it lattice processing. So the Lasp execution here is a directed graph of CRDTs connected by operations. So this is the paper we published in 2015 in the Symposium on Principles and Practice Declarative Programming. So this was the first language that composed CRDTs and kept strong eventual consistency. So the programmer looks at this, it looks like a pure functional language, but it's distributed and fault tolerant, okay? And we have scaled this up to 1,000 nodes on Amazon Web Services. It's very expensive, but now we can use Grid 5000. So this paper won the 10-year most influential paper award of this. So Lasp execution obeys the Calm theorem. Okay? It's functional, and adding CRDTs makes it fault tolerant. So a little bit of how it works. So a simple Lasp programming is a directed acyclic graph of CRDTs. So here I have two sets, for example, and there's a map in between. So it kind of looks like an incremental database. These sets are like relations, but they can be changing over time, and the map will track. So if S1 changes, S2 will follow it. So this whole system was implemented in Erlang. So this would be the syntax for that operation. Now you declare S1, layer S2, you can actually put stuff in the set. So 1, 2, 3, S1, and then you can create a map. So the map is actually a process. Huh? It's a living process that connects the two data structures, S1 and S2. And we proved the theorem. I told you I was going to show you some theorems. So assuming we have a crash stop model and at least one replica is correct, assuming we have a directed acyclic Lasp program, then the theorem is it satisfies strong eventual consistency. So the CRDTs do it, but the whole program also. So this was, and we actually proved this. It's one of the rare times that we actually made it, that I made a mathematical proof. Okay. So, but actually a lot is happening when it runs. So the programmer sees this. The set T is a map of the set S, but on the runtime, you have n replicas here, which are on different nodes. The replicas are doing replica-to-replica communication arbitrarily, and the map is, when you update SA, it's each of these map is updating the TA. So it's completely asynchronous. There's nothing really synchronized. Information is kind of flowing through this thing, but it obeys like it to the programmer. It looks exactly like a simple functional statement. Okay, so that there's a mapping between T and S, but in the distributed execution, there's a lot of stuff going on. Okay, so let me give you a bigger example. So this was done in an EU project called SyncFree. And we had a partner in that project called Rovio. You may have heard of them because they made this thing called Angry Birds, which you may have heard of, which was a flash in the pan. So of course, Rovio had problems when Angry Birds all of a sudden was less successful after some time. Rovio had a lot of problems, okay? But while it was successful, they were doing very well. So this is called an ad counter. So I have mobile games running on mobile phones, and I want to sell advertisement space. So how do you pay it? It depends on how many clients see, how many views there are. So I say, I want 100,000, I'm paying for 100,000 views, so for 500,000 views. And the clients will go offline and back online, and the ads are still displayed, even if the clients go off and online. And of course, the connectivity of mobile phones is very erratic. That doesn't matter for convergent consistency, okay? It's all eventual. The thing will still converge. So here we have an arbitrary number of clients. We implemented the contracts and the ads as OR sets. We have counters. So these are G counters in CRDTs. And we disable the ad when it reaches the number of views that it got. So this is a long-lived application that is completely monotonic, distributed fault-tolerant application. So here's kind of the core computation. I have the ads, contracts. I make a Cartesian product, then I make a filter. So I will take the ads that have contracts. So basically, it's very similar to joins in a distributed database, okay? So this is kind of like a dynamic database with joins. And the whole application looks kind of like this. Okay, so new ads can come in anytime, new contracts. This is kind of the heart. These counters are running. So there's a number of them for the different ads. And they have occasional communication with the client. So here you can have millions of clients, okay? So this thing, we implemented it, and we simulated it at pretty large scale. And we actually scaled it up. So this whole implementation, so we had a first implementation of Lasp, which was the one we did in 2015. So we used a part of the React database, a consistent hashed ring. And then 2 years later, so Chris made a communication software called Partisan, which is using hybrid gossip. This thing actually still exists today. This is a library that exists, and it's being used just by itself as a communication layer. So this is actually an industrial output, the system, but we used it as a part of our hybrid gossip Lasp. So we scaled it up to 1,000 nodes on Amazon Cloud. That was hard. That was really hard. I mean, there's this orchestration tool called Kubernetes, But when you get to a very large number of nodes, it gets very flaky. So basically what we did was we implemented a workflow CRDT. So the whole creation of the infrastructure is also convergent. So we actually took advantage of the convergent nature of CRDTs to create a workflow CRDT. And here you can see some of the performance. So this is the number of gigabytes transmitted, the number of clients, so up to 1,000 clients. And so the DC is the data center. S/S means it's state-based, like I showed you. But there's an efficient optimization called delta-based, where you only, when you do the replica-to-replica communication, you only transmit the changes, the deltas. So that's the delta state-based. So this one is more efficient. So that the data center one would not go beyond 256. But here, this one goes up to, we did it up to 1,034 nodes. So this was in 2017, okay? Using we scaled it up. We've actually paid Amazon for this. When I saw Jonathan Schmitz in his PhD, he did also very large experiments, but he used Grid 5000, so he didn't pay anything. But for this, we paid 9,000 euros, okay, to do this. This paper made Amazon 9,000 euros richer, okay? And it cost us this paper. Okay, so maybe I'm pretty good on time here. So concluding from this, if you want to do large-scale fault-tolerant distributed programming, there's basically two ways. You can use consensus, which has existed since 1989. Thank you, Leslie Lamport. Or you can use a convergence architecture. So this is something we understand since 2011. Interestingly, these two were done independently. So the CRDTs were invented by a group in France, headed by Mark Shapiro, and the comp theorem was in UC Berkeley in 2011 by a guy named, I think it's Joseph Hellerstein, but Peter Alvaro is the main guy. But they didn't actually prove it then. It was proved a few years later. It was a hypothesis that they made. It seems to be like this, and it was like that. So fault-tolerant, distributed, free. So this is a very active research area. People are using CRDTs in more and more places. So many legacy systems using consensus are actually being replaced bit by bit by CRDTs. So it's widely already used in industry. So there's no more need for proof concept. So what will happen in the future? So in my view, there's always going to be a role for consensus, because if your system is really very non-monotonic, and even monotonic systems often have a small piece that's non-monotonic. If you have a voting system, for example, at some point, the final result of the vote is a non-monotonic thing. So you have to do a little bit of consensus, but much less than what people think. And another lesson is that languages are important for distributed systems. Many people in this distributed system community, they think languages are totally irrelevant, okay? Talk to them. They believe doesn't care the languages. The algorithms are like that. But no, we're showing here, if you do a functional approach, functional programming, you get a clear benefit in the distributed system by using a functional language that's monotonic and concurrent and fault tolerant. So final conclusion, so this convergence is indeed becoming a credible alternative. So there's basically two ways to do these kind of distributed systems. So that's my final conclusion. And there's also a little bibliography if you want to look at stuff. So thank you.